So guys, now we discuss about derivative as a rate measure. In the previous lecture already we studied about equation of tangent and equation of flow. So next part of the derivative, which is derivative as a rate measure. Derivative of a rate measure means, here the definition of derivative of rate measure is the instantaneous rate of change of with respect to t is defined as f dash of t is equals to limit h tends to 0 f of a plus h minus f of a upon h, which is the exact definition of derivative. There is the rate of change, rate measure. It means that to determine the rate of change of quantity. Also we can say that to determine the rate of change of quantity. How to increase the quantity? If A is any circle, O is the center of circle, distance of O from P which is a radius. If the radius is increases, then area also increase, which is a best example, the rate of change of quantity. Anotherly, we can say slope of tangent is a rate measure. So now first we know about rate measure or rate of change of. So if y is equals to f of x be any curve or be a given functions, when we differentiate with respect to x, then we can say that dy upon dx is equals to f dash of x. It means that the rate of change of y with respect to x. It is a rate measure, rate of change of y with respect to x. The change is also in increasing order. If we can write dy upon dt, then we can say that rate of change of y with respect to time, with respect to t. When t is time, then we can say that the rate of change of y with respect to time t. So change in also differentiable form means d upon dt. So the first example of derivative as a rate measure, which is example number first, is a stone is dropped into a quiet lake. You know about stone, you know very well about quiet lake. If a stone is dropped in a quiet lake and waves in the form of circles and waves in form of circles are generated, radius of circular wave increases at the rate of 5 centimeter per second. At the instant when the radius of the circular wave is 8 centimeter, how fast is the area enclosed in increasing? Here we have to find how fast the area enclosed in increasing order. So it is simple to solve that, which is calculus. Stone is dropped in a quiet lake. After dropping stone in a quiet lake, there waves in the form of circular wave. When time increases, then radius also increases, and circular wave increases at the rate of time. Hence we can say that here we have to find the area of enclosed in increasing, which is area, rate of change of area with respect to time t. So here first waves form in the form of circles. Radius of a circular wave increases at the rate of 5 centimeter per second. It means that given that rate of change of radius r with respect to time t. So first we consider that let r be the radius of circular wave or circle. After that, a be the area of circular wave or circles. Now, by the given condition, rate of change of radius of a circular wave increases. Increase means here in a radius there are change which with respect to time t, rate of change of radius with respect to time t is 5 centimeter per second. It means that given that dr upon dt is equals to 5 centimeter per second, we have to find at the instant when radius of the circular wave is 8 centimeter, how fast is the area enclosed in increasing. Means we have to find dA upon dt when radius is equals to r centimeter. So now we first know about the area of circles. We know that area of circle A is equals to, which is denoted by the area of circular wave, pi r square. Area of circle, which is, so if we differentiate with respect to t, then we can write dA upon dt is equals to pi is constant function, derivative with respect to t, r square. R is a radius. T means time. We have to find derivative with respect to time, but r is a radius. Hence, if we consider that r is a function of t, then we can take a derivative of r square, which is 2r, and again derivative of r, which is dr by dt. So here 2 into pi, which is 2 pi r into dr upon dt. We have to find area, changing area when the radius is 8 centimeter. So if we take 2 pi r dr by dt and the value of dr by dt, which 5. So we can write 5 into 2, 10 pi r. We have to find rate of change of area when r is equals to 8. We can write it, r is equals to 8. We can write it 2 pi 8 into 5. So, or we can write 10 pi into 8. 10 into 8, which is 80. 80 pi is a required rate of change of area with respect to time t, or which is a required and instantaneous when radius of the circular wave is 8 centimeter. Then the area increase at the rate of 80 pi centimeter square per second in the increasing order. So again, the next example, question number 2 is, the volume of the spherical ball is increasing at the rate of 4 pi per cc per second. Find the rate at which the radius and surface area are changing when the volume is 288 pi per second. First we consider that here V be the volume of spherical ball. V be the volume of spherical ball and R be the radius of spherical ball. So again, here given that surface area, which is S be the surface area of spherical ball. Now the volume of spherical ball is increasing at the rate of 4 pi per second. It means that given that rate of change of volume of spherical ball means dV upon dt is equals to 4 pi cc per second, or dV upon dt is equals to 4 pi. Here again we have to find the rate at which the radius and the surface area are changing. Hence we have to find rate at which the radius and surface area are changing when the volume is 288 pi cc. It means that we have to find ds upon dt when volume is 288 cc is equals to what? So first we know that, or we have about the volume of spherical ball, V is equals to 4 by 3 pi r cube, which is equation number 1. Volume of spherical ball, which is 4 by 3 pi r cube. If we differentiate with respect to t, the derivative with respect to the v of v, which is dv upon dt, 4 by 3 pi, which is constant, and we take a derivative with respect to t of r cube. T, which is time, r be the radius. So if we consider that r is a function of t, then we can write the derivative, which is dv upon dt, is equals to 4 by 3 pi into derivative of r cube, which is 3r square. Here 3 cancel, we can write 4 pi r square, which is, or 4 pi r square into dr upon dt, We know that the rate of change of volume with respect to t dv upon dt is 4 pi, hence we can write here 4 pi again. Here 4 pi get cancel, we can write, if we take this whole term right side, we can write dr upon dt is equals to 4 pi upon 4 pi r square. 4 pi get cancel, which is dr upon dt is equals to 1 upon r square. But we have to find the radius and the surface area changing when volume is 288 pi. So here first we have to find rate of change of radius with respect to time t, which means that dr upon dt when r is equals to 288 pi. When volume is 288 pi, we can write it from equation 1, v, the value of v, which is 288 pi, or we can write when v is equals to 288 pi. From equation 1 we can write 4 by 3 pi r cube is equals to 288 pi. If we shift whole terms right side, we can write r cube is equals to 288 pi into 3 upon 4 pi. Here pi get cancelled. We can write r cube is equals to 4 1. We can write 72. 72 into 3, we can write 216, which is the value of r cube. If we take cube root of both sides, taking cube root of both sides, we can write the value of r, which is 6. Here radius r is equals to 6. So from equation 2 we can write here dr upon dt. Therefore equation 2 become dr upon dt is equals to 1 upon r square, means 6 square, which is 1 upon 36, which is a rate of change of radius with respect to time t. Now we find again the rate of change of surface area with respect to time t. It means that ds upon dt. So we know that S be the surface area, and surface area of spherical ball, which is S, is equals to 4 pi r square. 4 pi r square. If we differentiate with respect to time t, we can write ds upon dt, which is the required rate of change of surface area, is equals to 4 pi derivative of r square, derivative with respect to t of r square, t, which is time, r is radius. If we consider that r is the function of t, then we can write 4 pi derivative of r square, which is 2r into dr by dt. We know that the value of dr by dt, which is 1 upon 36. 4 pi 2 into radius, which is r is equals to 6, and dr by dt is 1 upon 36. So 6 1, which is 18, 6. We can write it 2 1 6 3, means 4 pi by 3, which is the rate of change of displacement with respect to time t, and dr upon dt is equals to 1 upon 36, which is a required answer A and required answer B, the rate of at which the radius changing dr upon dt is 1 upon 36 and surface area changing with volume is 288 pi cc, ds upon dt is 4 pi upon 3. So the next example, example number 3, which is water is being poured at the rate of 36 meter cube per second in a cylindrical vessel of base radius is 3 meter. Here we have to find the rate at which water level increasing or water level rising. So it is clear that here we have to find rate of change of water level. So we can consider that level of water be the h height of the water level. So first we consider that r be the radius of the base. R be the radius of the base. After that, here water is being poured at the rate of 36 meter cube per second. It means that so h be the height of water level, we can say that. After that, v be the volume of cylindrical vessel, volume of cylindrical vessel. So we know that volume of cylindrical vessel V is equals to pi r square h. Pi r square h. So we know that equation number 1. But given that here radius r is equals to 3. So we can write it V is equals to pi into 3 square h, or V is equals to 9 pi h. If we differentiate with respect to t, then we can find dv upon dt is equals to 9 pi derivative of t with respect to h, or we can write directly dh upon dt. So here we have to find dh upon dt. And given that water is being poured at the rate of 36 meter cube per second, it means that so also we can write dv upon dt is equals to 36 meter cube per second. If we substitute the value of dv upon dt, which is 36 meter cube per second, we can write 36 is equals to 9 pi into dh upon dt. So here, if we take the 9 pi, right side we can write dh upon dt is equals to, it means the rate of change of water level. Height means h be the height of water level. dh upon dt is equals to 36 upon 9 pi. 9 is 1 and 36 4. We can write dh upon dt is equals to 4 pi meter per second, which is a required answer. Rate at which the water level rising when dv upon dt 36 meter cube per second and radius r is equals to 3 meters. We can write here 4 upon pi meter per second. So the next example, which is example number 4, is a man of height 180 centimeter. One man is heighted, which height is 180 centimeter. Is moving away from a lamp post at the rate of 1.2 meter per second. The man which is moving away from the lamp post at the rate of moving away from lamp post, which is at the rate of 1.2 meter per second. If we consider that this is a lamp post, this is a land, a man which move, OA be the lamp post, man which is moving away from the lamppost. So is let's start from lamppost with the rate of 1.2 meter per second, means it is go away from at the rate of 1.2 meter per second. So here n be the height of man, or we can write OA or OP be the height of lamppost. Here OA be the height of, OP be the height of lamppost, MN be the height of man. Here M we can write it OA OB, land which is OB, OB be the shadow of lamppost, or we can consider OA, OA be the MN, MB be the shadow of man. We consider that the shadow of man which is x, length of shadow of man which is x, and distance of OM be the y, hence length of shadow of lamppost is OM plus MB which is x plus y or y plus x. So here now write that OA be the lamp post. After that MN be the man, MN be the man. After that we consider that MN which is MN is equals to x. So again x be the length, MB, consider that x which is shadow of man. After that OM is equals to y, OM is equals to y. So we can write again that here given that man is moving away from the lamppost, it means that given that man is moving away from the lamppost at the rate of 1.2 meter per second, means dy upon dt is equals to 1.2 meter per second. And it is clear that the lengthening shadow of the man, rate at which lengthening shadow of a man is equals to dx upon dt. So here we have to find his shadow is lengthening and tip of the shadow is moving. Now B is the tip of shadow, B is the tip of shadow. We have to find his shadow is lengthening, his means, and his distance from lamppost which is OB, distance of tip of shadow OB means x plus y. So now x upon 1.8 is equals to x upon 1.8, 180 centimeter converted into meter, 180 centimeter which is 1.8 meter is equals to length of shadow or tip of the shadow, distance from lamppost which is OB is x plus y upon 4.5. So if we take a cross product of both, we can write 4.5x is equals to 1.8 into x plus y. We can write it multiplying by 10, both sides we can write it 45 also. 4.45x is equals to 18x plus 18y also. So now if we divide Now in both side we can write, or directly we can write 5x is equals to 2x plus 2y. If we take this 2x left side, we can write 5x minus 2x is equals to 2y. Hence 2y is equals to 3x, or we can write y is equals to 3 by 2x. So if we differentiate with respect to time t, we can write the derivative of y, which is dy by dt is equals to 3 by 2 into dx by dt. So we know that the value of dy by dt, which is 1.2 meter per second, hence we can write 1.2 or dx upon dt into 3 by 2 is equals to 1.2, or dx upon dt is equals to 1.2 into 2 by 3. So here 3 is 1, 0.4. We can write dx upon dt is equals to 0.8 rate of change of shadow of the 0.8 meter per second. So also we have to find that rate at which the tip of the shadow which is moving is given by derivative with respect to t, which is x plus y is equals to dx by dt plus dy by dt. So here dx by dt, which is 0.8 meter per second, plus dy by dt, which is 1.2 meter per second. So 0.8 plus 1.2, which is 2.0 meter per second, which is hence the shadow is lengthening at the rate of 0.8 meter per second, and its tip is moving at the rate of 2 meter per second. 2.0 we can write it 2 meter per second. Now we discuss about velocity, acceleration and jerk. So here you know about velocity, acceleration, which is a physical quantity. So velocity means rate of change of displacement with respect to time t, or acceleration means rate of change of velocity with respect to time t is called as acceleration, and jerk means rate of change of acceleration. The rate of change of acceleration, some changes in the acceleration increasing order is called as jerk. So now we have two about velocity, acceleration and jerk. If we have to discuss about velocity, acceleration and jerk in simple format in the form of mathematical language, so here we know that about S be the displacement, V be the velocity, A be the acceleration, and jerk means the rate of change of acceleration. So here displacement, which is now first velocity. Velocity means rate of change of displacement with respect to time t. It means that v is equals to ds upon dt. Rate of change of displacement with respect to time t, which is velocity. ds upon dt means velocity. First order derivative of displacement, also we call as first order derivative of displacement, is velocity. Also about we know that acceleration. Acceleration means rate of change of velocity with respect to time t is called as acceleration. It means that if v is equals to ds upon dt, and if we differentiate with respect to time t, then we get dv upon dt is equals to d2s upon dt square. So we know that rate of change of velocity with respect to time t is called as acceleration, means dv upon dt, or a is equals to acceleration, or acceleration a is equals to dv upon dt or d2s upon dt square. Now the third part, which is jerk. The rate of change in acceleration, rate of change of acceleration with respect to time t is called as jerk. Also we can say that j is equals to d a upon dt, or we can write dA upon dt, which is d2s upon dt square. If we differentiate with respect to t, then jerk we can write at derivative of d2s upon dt square, which is d cube s upon dt cube, which is a jerk. It means that velocity v is equals to ds upon dt, acceleration a is equals to dv upon dt or d2s upon dt square, jerk j is equals to dA upon dt or dt d cube s upon dt cube. So now we take example which is based on the velocity, acceleration and jerk. So here example number first is a car is moving in such a way that the distance it covers is given by equation s is equals to 4t square plus 3t square. It means that here given that distance covered by the car in form of equation displacement s is equals to 4t square plus 3t, where is s is a meter and s is in meter and t is in second. What will be the velocity and acceleration of the car at time t is equals to 20 seconds? So here first we consider that v be the velocity, a be the acceleration. So here given that the distance covered by the car s is equals to 4t square plus 3t. So if we differentiate with respect to t, then we get ds upon dt is equals to 4 into derivative of t square, which is 2t, plus 3 into derivative of t, which is 1. 4 into 2, which is 8t, plus 3, which is ds upon dt, means v velocity of car. So if we again now we know that v is equals to 8t plus 3. If we again differentiate with respect to t, then we get dv upon dt is equals to 8 into derivative of t plus derivative of 3. So 8 into derivative of t, which is 1, plus derivative of 3, constant function is 0. Hence 8 into 1, 8 plus 0 is 8, which is acceleration of the car. So here we have to find velocity and acceleration of the car at time when t is equals to 20 seconds. When t is equals to 20 seconds, then velocity of the car v is equals to 8 into 20 plus 3, which is 160 plus 3, v is equals to 163, and acceleration when t is equals to 20, a is equals to 8 meter per second square, or velocity which is meter per second. So here the displacement of a particle at time t is given by s is equals to 2t cube minus 5t square plus 4t minus 3. Here first we consider that s be the displacement of particle, v be the velocity of a particle, a be the acceleration of particle. So here given that displacement which is s is equals to 2t cube minus 5t square plus 4t minus 3. If we differentiate this displacement with respect to t, then we get ds upon dt is equals to 2 into derivative of t cube, which is 3t square, minus 5 into derivative of t square, which is 2t, plus 4 into derivative of t, which is 1, minus derivative of 3 is 0. 3 into 2, which is 6t square, minus 10t, plus 4, which is a ds upon dt, rate of change of displacement with respect to time t, which is a velocity. So, if we differentiate velocity, differentiate with respect to t, then we can write dv upon dt is equals to derivative 6 into derivative of t square minus 10 into derivative of t plus derivative of 4. So here derivative of t square, which is 6 into 2t minus 10 into 1 plus derivative of 4 constant function 0. Hence dv upon dt, rate of change of velocity with respect to time t, is acceleration, and a is equals to 12t minus 10. But we have to find time when the acceleration is 14 feet per second square. We have to find acceleration when t is equals to, given that 14 feet per second square, 14 feet per second square. So if we have to find acceleration when time is t is equals to 14 feet per second square, then a become 12 into 14 minus 10. 14 into 12. So acceleration when 14 feet second square means a is equals to 14 is equals to 12t minus 10. We have to find time on t when a is equals to 14 feet per second square. So here 12t minus 10. If we take this 10 right side, we can write 14 plus 10 is equals to 12t. 12t is equals to 24. Then t is equals to 2 second. We have to find again velocity and displacement when at that time is when t is equal to t. Now we have to find velocity and displacement when t is equals to 2. We know that v is equals to 6t square means 6 into 2 square minus 10 into 2 plus 4. 2 into 2 square, which is 4. 6 into 2 4 minus 10 into 2, which is 20 plus 4. 24 plus 4, which is 28 minus 20 plus 4, which is minus 16. 24 minus 16, 8. Now we have to find displacement when t is equals to feet per second. So here we have to find displacement when t is equals to 2. Now we know that displacement s is equals to, displacement 2t cube minus 5t square plus 4t minus 3. We have to find displacement when t is equals to 2. We can write s is equals to 2 into 2 cube minus 5 into 2 square plus 4 into 2 minus 3. 2 cube means 2 into 8 minus 5 into 4 plus 4 into 2 8 minus 3. 8 minus 3 which is 5. 16 minus 20 plus 5. We can write it 20 plus 5 which is 16 minus 15 which is 1 feet. Displacement is given 1 feet. So here, hence acceleration A is equals to 20 minus 10. When we have to find acceleration when 40 feet per second square, the time t is equals to 2 seconds, velocity 8 feet per second, and displacement is s is equals to 1 feet.